This is my pocket. Can everyone hear me?
Yeah.
Great. Got it? Okay.
Okay, so last but not least, sort of sad actually, because it's the last in-person talk of QIP, but let's go to the talk of Sam Slezak, who's going to talk about Eigenstate Thermalization and quantum Metropolis sampling.
Thank you. Yeah, so I'm Sam Slezak, and today I'll be telling you about some joint work I did with my co-author, Elizabeth Crosson, on Eigenstate Thermalization and quantum Metropolis sampling. Okay. And so the context of this talk is we want to be able to simulate properties of quantum systems, and by that I mean calculate properties of interest. This is very useful for things like materials science, chemistry, basic physics, but in general it's hard because due to the exponential size of the Hilbert space of composite quantum systems. And so, nonetheless, there's some methods to get around that for some systems, and the ones we're going to talk about in this talk are Markov chain Monte Carlo methods, quantum computers, their combination in a technique called quantum Metropolis sampling, and then we're going to apply it to a class of thermalizing quantum systems, namely ones that satisfy the Eigenstate Thermalization hypothesis, and our result is that leads to an efficient simulation technique at constant temperatures. Okay, and so I'm not going to review quantum computing to this audience, but I will briefly review Markov chain Monte Carlo methods. So these are a method for sampling from probability distribution of interest. And so we have a random walk over a state space described by a stochastic matrix, Pij, and under some standard assumptions, that's going to converge to a unique limiting distribution given by pi. And the thing is, the walk is going to approach the limiting distribution with a number of steps. And so the idea is this gives us method for sampling from pi, because if you wait long enough, you know that the distribution of the output of the walk is going to be close to the limiting distribution. But this leaves open the question of how long we have to wait. And so this is characterized in the Markov chain literature by something called the mixing time. And this is given by the minimum time it takes over conditioned on we starting at the worst starting position that we're guaranteed to be within a certain distance in the total variation distance, which is a standard metric on probability distributions, of the limiting distribution. And so this is kind of the main object of interest in Markov chain analysis. Okay, and so an example of Markov chain Monte Carlo methods in classical physics is given by the Metropolis Hastings walk, which is used to sample from the Boltzmann distribution of some system. And so the idea is with this walk is we're given an initial proposal distribution, Mij, so this is some other stochastic matrix. It's generally symmetric, or no, in this case it has to be symmetric. And we modify it by these Metropolis Hastings weights that are given right here. And in practice, numerically, we can do this by rejecting with some probability, rejecting proposed moves with some probability. And the idea is once we have these Metropolis Hastings weights on the off-diagonal elements of this stochastic matrix, this is guaranteed to converge to the steady state distribution up here because it satisfies detailed balance with respect to that distribution. Okay, and then, so there are methods so that's a method for sampling from simulating a classical physical system, and it turns out we can extend these methods to quantum systems, or some quantum systems via the quantum to classical mapping, which was introduced by Suzuki in 1976, and the idea is we have a d-dimensional quantum system, or the partition function for a d-dimensional quantum system, and we can map that to a partition function for a d+1 dimensional classical system. And models that allow you to do this, or models that admit this mapping, are generally referred to as not having a sign problem. But I do just want to characterize that, or to mention that all because a model admits this quantum to classical mapping doesn't mean you can automatically calculate properties of interest about it, because this classical distribution that it gets mapped to could still be very hard to sample from. But nonetheless, if a model does have the sign problem, you just can't even get your foot in the door. These techniques don't really work. And so the question is, can we use Markov chain Monte Carlo methods on models that have the sign problem? And it turns out the answer is yes, if we have a quantum computer. And so there was a quantum algorithm introduced by Kristen Temi et al. In 2010 called quantum Metropolis sampling. And the idea behind this algorithm is, in a certain limit at least, it can be viewed as a random walk over the energy eigenbasis of a Hamiltonian. And so we have some quantum system with its energy eigenvectors, and we consider the state space of a Markov chain to be the energy eigenvectors of a Hamiltonian, the steady state distribution to be the thermal state populations in the energy eigenbasis of the Hamiltonian. And what this algorithm essentially does in a certain limit is it takes as input an energy eigenstate and outputs a mixture over energy eigenstates, where the mixture coefficient is given by a stochastic matrix. And this stochastic matrix will converge to the steady state given up here, which means the whole thing is converging to the thermal state. Okay, and so I'm going to give a brief overview of this algorithm. I'm not going to go too much into the weeds, but there's a few important things I want to highlight. So we have a system register, and then we have two energy registers. And we're going to assume that the first energy register already has an R-bit encoding of the energy of the current eigenstate that we're in. And so what we do is first we apply a unitary from some ensemble with a probability U, or probability given by PU. And then we do phase estimation on the system register and the third energy register. And then we do this kind of magical quantum channel over here that basically what this does is it puts Metropolis Hastings weights according to these two energies into the mixture. And so what you end up with is something that looks very much like the classical Metropolis sampling matrix, where we have this proposal distribution over here that is kind of like that M matrix I wrote down, where that's going to be related to this ensemble of unitaries that we're perturbing the system with. And then this F channel is put on the magical Metropolis Hastings weights that are going to make sure this thing converges to the thermal state. Okay, and so in their paper, they showed that you can do one application of this channel in polynomial time. And so this leaves open, what's the mixing time? How long is it going to take to converge to the thermal state? And this is hard to characterize because virtually all mixing proofs, at least classically, require knowledge of the stochastic matrix. If you don't know what the stochastic matrix is, you're not going to be able to tell what the mixing time is. And in our case, what we need to know to even write down what the stochastic matrix is the matrix elements of these unitaries that we've applied in the energy eigenbasis of the Hamiltonian. Which, you might as well, to do that, you have to, in general, diagonalize the Hamiltonian. If you can do that, there's really no point in doing any of this. You know everything. Okay, so, but nonetheless, we're going to try and make progress on this. We're going to take a direction, an observation in the original paper of quantum metropolis sampling, where they said that classically, it always seems possible to devise an update strategy for a Markov chain that will mix rapidly if the underlying physical system thermalizes in polynomial time. And so with that in mind, we're going to take a detour and we're going to look at quantum systems that thermalize. Okay, and our operational definition of thermalization is going to be a system thermalizes if it equilibrates to a state that only depends on certain macroscopic quantities. And so for the example, this is brick. It wouldn't matter which side of this brick was hot or cold. It would equilibrate to the same temperature, which was equal to energy densities throughout, regardless, right? And so a mechanism for this to happen in closed quantum systems is given by something called the Eigenstate Thermalization hypothesis. And I'm going to give two versions of ETH in this talk. This first one is one that makes more sense to me. The second one is more useful in our proof. And so this first one is basically you take an excited energy eigenstate of the Hamiltonian, and you look at its reduced density matrices on subsystems, and that is very, very close to the reduced density matrix of a thermal state on the full system. And so in this sense, excited eigenstates are thermal, and that all of their RDMs look thermal. And this directly leads to subsystem thermalization in closed systems, which means that if you have a closed system and you just look at a subsystem, the rest of the system will act as a bath on the subsystem. And that's why ETH was originally proposed. Okay, so that's one formulation of it. But it turns there's another one that's equivalent, that's much more useful for our proof. So rather than focusing on RDMs, we're going to focus on a property of all local observables. And so another way to formulate ETH is an ansatz for the matrix elements of observables in the energy eigenbasis of the Hamiltonian. And so some things I want to point out is we have this smooth function controlling the diagonal elements. And then what's most important for us is going to be these off-diagonal elements. And so we have this part here with an exponentially small factor, where S is going to be the thermodynamic entropy at energy E. So e to the minus S, we have this exponentially small factor. And then we have this smooth envelope function F, that's a function of omega, the energy difference, and E bar, the average energy. And then we have some IID random variables. And this is great, because this gives us information about the matrix elements. So, we just replace this with U. Now we have information about matrix elements. Okay, so we plug this into the previous expression we derived for the quantum metropolis sampling stochastic matrix, and we end up with this. And this is great, because now we actually have something we can potentially analyze. But, it seems like it's going to probably strongly depend on this, this F envelope function. So we're going to take a look at that on the next page. And so this was introduced by Srednicki in one of his original papers on ETH in 1998. And he explains that it has, postulates that it has 3 distinct regions. And the one that's most important for us is this region of small energy difference, so omega close to 0, And we call it this delta RMT region, and RMT stands for random matrix theory, because ETH can be kind of the result, or ETH can kind of be seen as an extension of the results of random matrix theory. And within this small energy difference band, kind of exactly reproduces the results of random matrix theory. And the important thing is that this energy window, where the function is approximately constant, is inverse polynomial in the system size. And then there's two other pieces of the function that are cool, but they don't show up in our proof. I'm going to skip them for time. Okay, so now before jumping into the actual proof for why ETH systems will mix rapidly, I want to give you some intuition for what's going on. And so basically, what we have is a quasi 1D walk over the energy eigenbasis. And so we're basically taking expected step sizes of delta random matrix or delta RMT, and then after each step, none of the fine-grained mixing dynamics really matter, and it just kind of mixes locally with each step. And another reason why, another piece of intuition for why this is mixed rapidly is there's always almost always a non-negligible probability to decrease the energy, which means you don't get stuck on local minima. Okay, so now we're going to dive into the proof. Okay, and so rather than bounding the mixing time, we're going to focus on the gap. And so if we can lower down the spectral gap of the stochastic matrix via this equation down here, that can give us an upper bound in mixing times. So for the rest of this talk, we're going to be talking about spectral gaps rather than mixing times. Okay, and so the idea is we have this result from Modis and Rondel in 2002, where you can lower down the gap of a stochastic matrix if you can lower down the gaps of this ensemble of other stochastic matrices that you define from this matrix, and we'll talk about that we'll talk about this right now. So basically what we're going to do is we're going to divide up the state space into a bunch of overlapping subsets. And so all of these subsets are going to be delta RMT with energy windows. And you can see they kind of overlap, like at chi1 and chi2 have some overlap. And then we're going to define an ensemble of new Markov chains. So there's going to be one chain, this P sub H M N, that's going to be transitioning between the new subsets that we've defined. And then there's going to be a host of other chains that are going to be transitioning in between energy eigenstates within each subset, or I'm going to call them blocks from now on, within each block. Okay, and if we can lower down the gaps on all of these chains separately, we can get a lower bound on the whole thing. Okay, so now this inner block chain is really simple, So this is the one that transitions between the states in the block. It's the same stochastic matrix, except if you were going to leave the block, you just stay where you are. Okay, and then the outer block chain is a little more complicated. The probability to transition between two subsets is going to be the steady state mass of the intersection of the two subsets divided by the steady state mass of the subset you're currently in, and times 1 over some factor theta. This is just 2 in our construction, so we're going to ignore it from now on. Okay, and now we're going to do all of the inner block chains simultaneously. So we're first going to make some approximations. So because the energies are close, the Metropolis factor can be approximated as 1, and any deviations away can be easily dealt with later. Yeah, and then we're going to take e to the minus thermodynamic entropy to just be 1 over the multiplicity of the block, the number of the states in that block. And then by assumption, the f function, this envelope function, is constant within these delta RMT with blocks, so we just take it to be constant. And then we're really left with some constant times some random variables. And then so what this really reduces to is a random walk on a fully connected graph with random edge weights. And the intuition for why this thing is going to have a big gap is if you remove all of the low capacity edges, we're left with a subgraph of big capacity edges that ends up being a random graph, ends up being an Erdos-Renyi random graph. And these things have a constant gap with high probability. And so with that, we do a Markov chain comparison technique between these two things, and we end up showing that the gaps of all these PM matrices are lower bounded by a constant with a probability that approaches 1 as the system size increases. Okay, now for the outer block, we don't have to do as much work because what we're really trying to do is we have a polynomial sized state space. So our state space is norm of H divided by delta RMT, the widths of each of these blocks, or at least proportional to it, probably times 2. And so that state space is polynomial size in the system. We want a mixing time that's polynomial in the system. So really all we have to do, and so we have to show that this thing is going to have an inverse polynomial gap when it has a polynomial sized state space. For that not to be the case, the chain would have to be basically disconnected. So what we use is a very flexible mixing analysis technique that makes minimal assumptions about what the steady state actually looks like. And we end up with a gap that's lower bounded as essentially the size of the state, or the inverse of the size of the state space cubed, times this parameter k. And this parameter k is related to how fast the density of states can change. And so k inverse for us is essentially an upper bound on how fast the density of states can change. Because the density of states is changing extremely rapidly, then this intersection could be much, much smaller than this denominator, and that could lead to like a disconnected chain, and that would be bad for us. So this k parameter, it's a bound on how fast the density of states changes, comes into our proof. Okay, and then putting it all together, all of the inner block chains were lower bounded by a constant. The gap of the outer block chain is lower bounded by this k delta RMT cubed over norm, or delta RMT over norm of h cubed. And so now we want to convert it to mixing time. And so for that, we use this formula up here. It's related to the inverse of the gap and the logarithm of the smallest steady state population. And so we can upper bound the log, like the log of pi min inverse as beta norm of h plus n. And then this is going to be a constant temperature result for reasons I'll explain on the next slide. So we're just going to take beta to be O of 1. And we're also just going to assume for simplicity of presentation that norm of h scaling faster than n. And we end up with this bound down here for the mixing time, where it depends on the k inverse, so how fast, which is related to how fast the density of states can change, and then the norm of h to the fourth and delta RMT cubed. Okay. And so now maybe some of you are thinking like, hey, couldn't this simulate ground states in polynomial time? Well, the answer is no, because ETH is only going to hold in the bulk of the spectrum. And so this technique is only going to work when the temperature is high enough such that most of the steady state mass of the thermal state is away from the sides of the spectrum. Okay, and then some future things we'd like to do with this. We'd like to ascertain how much the classical analysis can be extended to the case of more realistic phase estimation. And just more generally, like when can we use classical techniques, classical Markov chain analysis techniques to analyze quantum channels? And also classically, Glauber dynamics Markov chains are used as a model for physical thermalization. What can we learn about physical thermalization from studying quantum metropolis? With that, I will conclude.
Okay, so thank you very much for this very interesting talk. Do you have any questions? In the meantime, I have one of mine. You are using gap to bound the mixing time of this process all the time. And I mean, that's pretty useful, but there's some different quantity that can be used to estimate the mixing time, which is a bit, which provides some tighter estimate, which is that provides a tighter estimate, which will be like the log Sobolev constant or modified logarithmic Sobolev constant.
Sure, yeah.
Have you tried something like that? Because I guess it's usually much more complicated to work with that, but have you tried this?
So MLSI, it's kind of like it contracts, like it'll contract on average or something. Classically, I don't, at least in the book that Markov chains and mixing times, which is like my Bible for Markov chain analysis, I don't remember seeing that. There's stronger methods that avoid dealing with the gap. Like you can use like coupling methods that go directly to the mixing time, and you avoid this log 1 over pi min factor. But they're generally harder to apply, and most classical Markov chain analysis techniques just end up getting bound in the gap.
Yeah. Okay, thanks.
Thank you for the very nice talk. Just have a small question. ETH can be formulated in multiple versions. In particular, there is a strong version that requires that all eigenstates in the bulk of 8, and a weak one that just requires that they do with probability 1.
Yeah.
Which one do you need?
We assume strong. We assume strong. Yes. Yeah.
Thank you.
Okay, so if there are no more questions, let's thank Sam again and all the speakers of the session.